So what we're looking at in this section is rectangular coordinates. And you can kind of think of them rectangular coordinates as like a map. You're going to be looking for locations on this map. Now, the rectangular coordinate system, it's made up of two number lines. There's the familiar x-axis, and you might remember this from algebra. You also use this when you're working with negative numbers, but it's just your typical number line. And it extends on and on forever that way, and on forever this way. Then you have another axis. It's the vertical y-axis. And it's the same type of number line. It's just vertical. In fact, I'll move 0 over here so it's not in the way. But just a vertical number line. Now, you have what are called quadrants. So this is called quadrant 1, or Q1. This is quadrant 2, or Q2. This one's the third quadrant. And this one's the fourth quadrant. Finally, where the axes intersect, they intersect at the zeros. So this 0 here could represent the 0 for the y-axis. It could also represent the 0 for the x-axis. And this point of intersection is called the origin. So, as I mentioned earlier, we can kind of think as rectangular coordinates as sort of like a giant map. It's a landscape. And we have different locations on this map. So, is it okay if I erase this?
Go ahead.
So, when we talk about locating points, on this landscape, what we're going to do is we're going to look for what's called a coordinate pair. So choose a location on the x-axis. And let's say we choose a location on the y-axis. Well then, what we do, if we imagine lines coming out from these locations, where they would intersect, this is the point x, comma, y. And so we call that the coordinate pair. Now, another term for this you'll hear is called an ordered pair. And the reason they call it an ordered pair is that the order of these numbers matters. The x will always be first, and then after the comma, you will always see the y. So let's say we're looking for the ordered pair for some point P. And let's say P has this kind of location. I'll draw only part of the rectangular coordinates. You'll see this done from time to time. So let's say we have P located in this spot in space. So the way we try to come up with the ordered pair for P is we draw a line from P. And I'll do a second one. We'll do this sort of like an animation. That one's no good. This one maybe. Oh yeah, that's good. So what we'll do, we'll draw a line from P to X and from P directly across to Y. And these need to be perfectly vertical and perfectly horizontal. And when we draw those lines in, we hit the x-axis at 4. We're going to hit the y-axis at 2. So that means our xy is 4, 2. So questions about that? Now, there's different ways of locating points on these graphs. I'll show you the one that they use in the textbook. So let's say you're asked to plot 3, -2. Well, first off, the x-coordinate always first, y-coordinate always second. Then take a look at a portion of the rectangular plane. So the way we plot this is we can start from the origin. And from the origin, the first thing we're going to do, since x equals 3, we're going to go out to the value x equals 3. And because y equals -2, we'll then drop down to y equals -2. And that's going to give us our point. Questions about that? So let me do another one. Try to make this a -4 on this side. Not terribly symmetric. But we're not going to worry about it. It's hopefully the concept comes across. Now, the way we're going to do this again is first, we're going to start at the origin. Then we're going to come out to x is -2. And then because y is a +2, we'll travel up to y is 2. And that's going to be here. And so this gives us our point, -2, 2. So questions about that? So that's how we plot sort of on this landscape that we call the rectangular coordinate system. That's kind of how we move around that landscape. So next we're going to look at our equations. We're going to talk about this idea of graphing an equation. And this has come up. The book will ask you to graph curves and lines. It'll ask you to graph equations. They all mean the same thing. The one you want to kind of keep an eye out for is when it asks you to graph just individual points. Another kind of graph lines, graph curves, graph equations is you'll hear them also say graph all the points. All those mean the same thing. But every once in a while in the homework, they'll ask you to graph just individual points. And that's when they don't want the entire line, say. They just want those particular points. But we need to talk about how we're going to generate these points. And we need to talk about inputs and outputs. So this is where we have equations. Of two variables. So I'm going to give an example. Let's say we see this. This is sort of a common type of equation you'll see. What equations do is they establish or they claim there's a relationship between what you put in and what you put out. For example, if you say you cut down trees and you take them into a paper mill, well, the paper mill will turn the trees into paper. And that makes sense. So the input for the paper mill are trees. The output is going to be paper. So the idea of an equation is there's something we're putting in and we're getting something out. Think of it in terms of work. If you put in hours at work, what comes out of that is going to be, say, pay. So the hours are the input, pay is the output. So when we talk about equations, we want to identify the input and then identify what represents the output. And the input typically is going to be x, or what we call an independent variable. I'll explain why it's called independent. The reason we say X is independent is we get to choose it. Like, if we go back to our paper mill, well, what kind of wood do we want to use? Well, now to be fair, if you're actually doing this responsibly, there's only certain kinds of trees you can use. But in theory, you could just put anything in there. You could put in cottonwood trees, spruce trees. There's nothing in the universe that's going to stop you from trying, even if it might be a bad idea. So you get to choose this value. So next up is what we call the dependent variable. This is the output. Now, granted, as far as the universe is concerned, you can freely choose the input for that paper mill. It could be spruce, it could be myrtle, it could be palm trees. Why not? But the cosmos gets kind of the say in this. If you actually try putting palm trees into your paper mill, I mean, who knows what's going to come out of it? Actually, it might be really cool for all that I know. I honestly don't know anything about paper production. But whatever you put in, you don't necessarily get to control what comes out. What comes out is, well, what's going to come out, what kind of paper you get. And so you're dependent upon the cosmos to, well, whatever comes out of this paper mill according to the laws of physics and various things like this. So the output is going to depend on what you put in. So that's why we talk about y being a dependent variable. We can choose x, make x 10, for example, and that means this would become 3 times 10. When a number is next to a variable, it means times. 3 times 10 plus 1, and then whatever number we get, in this case 31, y has to be that number. In other words, we can choose x, but we don't get to also choose y. Once we've chosen x, then we're just going to get a y. It's just going to pop out. So y's value depends on our choice of x. It depends on the choice of x. So that's independent and that's dependent. So what oftentimes we do is we talk about what are called solutions. And solutions to these means there's an input and an output that are paired together. And they're the correct pairing. So for example, if I have an input of 10, well, 3 times 10 plus 1 is 31. So the output needs to be 31. But if I have an input of 10 and I have an output of 0, that's not going to make sense because 0 does not equal 3 times 10 plus 1. So one of the things you're going to be asked to do is verify these solutions. So, for example, I'll bring back our familiar equation here. Excuse me. Excuse me. Is that a solution? Well, first off, we want to identify our x and y. Again, x is always first. and y is always second. So we have this. Is it true that 16 does that in fact equal 3 times 5 plus 1? And what we're going to find out is, sure enough, it certainly does. So that means the input and output, they make sense. So 5/16 is a solution. So far, so good. But let's say we're given another ordered pair. So it'll be part B for this example. What about -5, -2? Well, is this going to be the solution? Well, start out. Y is 3x plus 1. Is -2 equal to 3 times -5 plus 1? Is that in fact true? Again, replacing y with -2, and again, it doesn't hurt to label these. So y is now -2, x is now -5. Does this actually hold? So is -2 equal to -15 plus 1? Well, it turns out this is -14. Those are not equal. They're not the same number. So this means -5, -2 is not a solution. Questions about that? All right. So that's the whole business with verifying solutions. Now what we can do is we can also generate ordered pairs. We're not just stuck having to test if something works or not. So we can create ordered pairs for a particular equation. So we're going to generate some ordered pairs. I'm going to generate 3. Now we have 3 x values, -7, 0, and 2. Now what I probably should have done in the beginning here, well, for what function are we generating ordered pairs? So let's come up with not a function, but a 2-variable equation, or equation with 2 variables. So let's use y, and that's going to be generated by, or equal to, x squared minus 3. We get a little fancy here. So again, x squared it's x times x. So that's going to be your x squared. Now, for x is -7, well, y will be -7 squared minus 3. So we're going to replace the x with -7. We're going to discover what y is. So y is just going to be y for now. And a typical thing you'll see when you replace a variable with a number, you'll oftentimes see parentheses. That's a very common thing. So -7 squared, that's -7 times -7, or +49 minus 3, or y is 46. So for this, when x is -7, y is 46. So we have an ordered pair of -7, 46. So there's our first ordered pair. Now let's generate another one. Let's try when x is 0. If I'm erasing too fast, please let me know. So this will be y. We have 0 squared. So 0 times 0 is 0. And that's going to be -3. So that means xy 0, -3. So this is sort of like just taking trees and tree stumps and putting them into the paper mill, and depending if we use different types of trees, we're going to get different types of paper. So one more tree to try. X is 2. Two times 2 is 4. And that is going to be 1. So xy is 1, 2. Oh, I'm sorry, I got that mixed. Ooh, sorry. Ooh, got it switched. X is 2, y is 1. Gotta remember, x is always first, y is always second. So that's how we can generate ordered pairs. And what we're going to do now is we're going to bring this idea of the rectangular coordinate plane, put that together with this ability now to generate ordered pairs, and we're going to graph these different equations. We're going to bring this all together. So the idea of graphing equations is going to be this. We'll generate ordered pairs. And then we'll plot those ordered pairs as points on the rectangular coordinate system. One thing, double check some terminology. There. So let's do an example. Let's say we have this. So we're going to use 5 points here. X is -2, -1, 0, 1, and 2. Now what's going on here is for each x, we're going to generate a y. X, generate a y. X, y, x, y, x, y. And then what we're going to do is take these 5 points. Once we have the x and the y's, we're going to graph these on that rectangular coordinate system. So first off, the way we typically set this up we're going to list all these x's. And then paired up, we're going to have our y. Now we want to remember what y stands for. Y is x squared. So that we don't want to forget. For x times x. So let's take -2. Well, if x is -2, y is -2 times -2, or +4. Now if x is -1, y is -1 times -1, or 1. Now if x is 0, then y is 0 times 0, or 0. If x is 1, y is 1 times 1, which equals 1. Finally, when x is 2, y will be 2 times 2, or 4. So that means our ordered pairs, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So now we're going to graph these. So let's take a look at this first point here, -2, 4. Well, first thing we're going to do, we start at the origin. And because the x, or the x coordinate, I'll mention that, I should mention that right now, we have a special term for x. We call it the x coordinate. And then we have a special term for y. It's the y coordinate. So with an x-coordinate of -2, that means we start at the origin, we go out to -2. With a y-coordinate of 4, we then go up to here where y is equal to 4. Next, we have -1 and 1. Again, start at the origin. X is -1, so we go to -1. And then y is going to be just 1, so we jump up to 1. So for this one, again, we're going to start at the origin, but the x-coordinate is 0, and the origin's at 0. So we're already there. We don't have to move. And then move up to y is 0. Well, wait a minute, y0 is also located here, so we don't move again. So this is the point, 0, 0. It's the origin itself. For this one, x is 1. Y is 1. So we go out to x is 1, up to y is 1. And then for 2, go out to x is 2, and up to y is 4. So these are the points. This is how we plot the points for this equation y equals x squared. The last thing we're going to do, we're going to connect the points from left to right. So this is going to give us a graph of y equals x squared. Well, a part of y equals x squared. It's the part that we can see using our graph points. So questions about that? All right. So let me do another one. And one of the things you're going to see in the homework is they're going to have you graph lines. And these lines are going to have arrows. And I think I have some, we can take a look at this. So there's a little confusion that can come up with how to graph these things, especially when you're graphing the lines. So let's say you have this. So let's say we're going to graph y equals x plus 2. I want to give you kind of a tip here. When we're working with lines, and this could be a little confusing because in the homework, they're going to have you work with 3 points. But to graph a line, you only really need 2. You only need 2 points to graph a line. So I'm going to pick, say, x equals -1. So I'm going to generate a point using x is -1. So that means y is x plus 2, or y is -1 plus 2, or y is equal to, well, -1 plus 2 is just 1. So we get a coordinate pair or ordered pair of -1, 1. So let's go with another one. Say x equals 1. So y is 1 plus 2, or y is equal to 3. And so that gives us 1, 3. So finally what we're going to do, we're going to graph this line. So the coordinate pair, we had a -1, 1. We can start at the origin. So we go out to -1, then we go up to 1. Then we have 1 and 3. So start at the origin, go to x equals 1, go up to y equals 3. And then we're going to connect these going from left to right. And with a line, what they're going to have you do, you can continue this line on with an arrow. Let's see here. And with an arrow. And this is how they're going to ask you to do it using the homework. They're going to have you do this in the homework. So I want to show you something. Let me switch over to the actual homework because there's a little confusion with this. So let me take a look here. Pardon me while I disappear for a moment. Let me pull up my version here. All right, there we go. So let me switch over to the share. Okay, here we go. So if we're going to graph something like this, the way you do it, and let's see, do they give us any points? They don't give us any, but you can generate some. But we have y equals 5x minus 2. So the way we graph this, we're going to double click on that double-headed arrow. So to go back here, this is selected. You're going to click on this, click on it again. Now a point that's on this line is actually going to be 0 and -2. So I'm just going to put my first point here. Nothing happens. It's like, well, all right, you put a point. Well, not nothing, there's a point. Now for the second point, say x is 1, you're going to get 3 for y. Now you get something that appears. And so this is the answer that you would submit. You would submit this as your answer. But you won't get this double-headed arrow, you won't get the line until you put this second point. Now, if you make a mistake, like, ooh, I don't know if I did that right, you can click on clear all. You want to clear the graph? Yes. So let's say I want to graph with some other points. Let's say x is 2. When x is 2, y is going to be 8. Oh, better get this clicked. 1, 2. X is 2, y is 8. And then when x is -2, well, that won't work. That'll be off the graph. Let's say x is -1, we'll get -7. And there we go. So that's how you work with these lines. You want to be careful with the terminology here. This says graph the equation. This is what they're looking for. They want you to graph the equation. If they say graph the equation or graph the line or graph all the points, they're looking for something like this. And if they say just graph specific points, well, then you just graph points here. Now let's see if we do this. See what this does. Let's go with this one. You might have to use 3 points. Oh, they're gonna have you do 2. Let's see, maybe. Oh no, you gotta be careful with this one. This is called a parabola. So again, the first point, not gonna see, oh, I gotta double click it. Not too dramatic. Second point, I'll go with this one. Ooh, gotta be careful. Now you can move this around. Oh, I see. Okay, so I'm sorry. I'm looking at something a little new here. So they want you, if you are going to do a parabola, at the graph, it's called the vertex, or the bottom point first. And then you can choose a second point. The bottom point is always the first point that you're going to be graphing. So clear all. I'll do that one more time. So let's say we have a parabola, and the bottom point is going to be sitting on the 5. So I want to graph that point first. And then if I have a second point, let's say, let's see, x minus 5 squared. So if we're at 7, that's going to be 4. There you go. And that would give you that parabola. But for lines, if you're doing lines, you're going to double click this one. Let's say you have a point that goes here for your line. If you have another ordered pair that's over here, so when you click the second point, that's when you get your line. It'll give you those, the head here and the arrowhead there. So just something to keep in mind when you're working with this section. All right.
Okay, so
Oh, I'm sorry.
no, I just got a little bit confused when you were pointing out like the graphs and where you want the lines to be and stuff. You were just showing an example. You weren't concluding, right?
Oh, I'm sorry.
You were just pointing out the examples.
It was just an example of it was on the homework assignment. One of the questions that was on there, and that one, the one they had was y equals 5x minus 2. Totally different from the one I did on the board. For that, what I did is I let x be -1. And they actually didn't give me x coordinates to start with. I just had to come up with them on my own. So that means I take this, we'll get that. And so what we have is xy is -1, -7. And then I went with x equals 1. we'll get y equals 3. And so that means we have an ordered pair with a different pin. 1, comma 3. So we have this one, and we have that one. So what I'm going to do, let me go back. I'll graph these. Let's take a look at that. So remember, we're using y equals 5x minus 2. So here we are. So this is y is 5x minus 2. So I'm going to use those 2 points. Now to graph the line, I click and click. And that gives me the double arrowhead. And then for x is -1 and y is -7, I start from the origin, I go to -1, and I drop down to -7. Now the other points, 1 and 3. So again, starting at the origin, 1 and 3. So x is 1, y is 3. I go to x is 1, and I go up to y is 3. And when I place the second point, then the line appears. And this is when I would hit submit. Let's see, I'll find out what this does. And I guess there you go. But that's how you would answer those questions. Again, clear all if you want to start over again. Does that help?
Yes, that helped me a lot.
Awesome. So yeah, that's where those points were coming from. But yeah, for these questions, they might ask you to choose an x value, and you just got to come up with at least 2 of them to graph this. So just something to keep in mind. Now, a number of the problems, what I've seen is I think they ask for 3. Some of them will ask you to graph 3 points, but to graph using that line tool, you only need 2, and that'll do it. All right. So the last thing to mention in this section is something called functions. And a function is a very special type of equation. And one thing that we do is we replace y with f of x. It's just sort of a formal thing. If you have, well, not really formal. It has its uses, and you'll see the uses shortly. But as far as computations go, you're going to do exactly the same thing. So y equals x squared. We can now represent this as f of x equals x squared. And then what this means for your ordered pairs, xy becomes x f of x. But as far as computations go, you're going to do exactly the same thing. Now, there's a little thing with the notation here, and this is kind of a neat thing, is let's say we have this. So this is our function. Now, in the past, we would have y instead of f of x. So what we'll do, you'll see us do this. When we have, say, x equals 2. Well, what you'll see, we'll start with f of x. But instead of writing, actually, we don't have to write this. There's a shortcut. We replace the x everywhere with 2. Like so. And so we'll get f of 2 is equal to 4 plus 4 plus 1, or f of 2 is equal to 9. And so what we'll get, the ordered pair, f of x, will be 2 f of 2. And then we know what f of 2 is. It's equal to a number. It's 9. So you'll see things like this. It's sort of a clever notation. I'm going to do another example where I really use this notation. But any questions about that?
Okay, I'm so sorry. I'm totally okay. So we're okay.
Okay.
You had 4 plus 4 plus 1 and then 9, and then you have the f2, and then I'm trying to figure out, okay, so if f was the 2, then it was 2 and then 9. Is that how you?
Oh, so I need to explain. There is one thing I need to kind of mention. So if f of 2 equals 9, and this is a kind of a confusing point. When we see parentheses, we usually need to think multiplication, which, like, for example, when we did the calculation up here, I can just see the shadow of the calculation on the board. So this here is 2 times 2. What's confusing about function notation is this looks like f times x, and it actually isn't. So
Yeah, that's why I got confused.
Yeah, this looks like the letter f or the variable f times the variable x. It's just kind of like, why would anybody do that? Well, you're right. Nobody would do that.
Okay.
One way you could think of this is a special symbol all to its own. And this is our function symbol. So it doesn't mean multiplication. In a way you can kind of think of it, this might seem a little, well, the drawing I'm going to do is silly. I think the idea is brilliant, but the drawing I'm going to do is going to look silly. But what this symbol kind of means, you could think of these parentheses as symbolizing factory doors.
Okay.
And so x is going to go into the doorway. And then f is basically f for function or f for factory. So x will go into the factory doors, and what goes on in this factory, what's going to happen to x? This is what's going to happen to x. And so when you see like f of 2, what that's going to mean is you have a 2, and the doors have been opened a bit. 2 is going in, and this function is going to process 2, and then something's going to pop out on the other side. The idea, I think, is really cool. My drawings might be going too far, but that's what this means. This is a symbol that means we're going to put x into this factory, and over here is what we see what's going to happen to x. And then once we simplify what happens to x, we do all the calculations, we're going to get an output.
Okay.
So yeah, it's very easy to think, oh, that looks like f times x. Totally different thing. Think of this as like the factory doors. F is going to process what goes through the doors. There's the number 2. It's going in, and it's going to get processed and converted or turned into, like, you know, like you take the wood and turn it into some paper or something like that.
Okay.
Oh, I hope that helps. But yeah, it gets kind of confusing. There's another one that comes up in mathematics. If you think about the rules for parentheses, you always do the calculations inside parentheses first. If you need multiple sets of parentheses, you could use multiples, or you can use brackets. So for example, a little bit of a diversion, but let's say we have 5 times 2 plus 1. You want to do this first and then divide by, say, 7. You do something like this. And if you want to multiply this whole thing by 3, you've got the brackets. And what they used to do, this is what they taught me in elementary school, if you want to divide this whole thing by 10, you would use, instead of another set of brackets, or instead of using another set of parentheses, you would use curly braces. They're backing away from using curly braces, though, even though they're fun to draw. They're backing away from that because you use these for something called set theory. In set theory is when you have a list of number types, say, or object types, and you do these different things with them. And so to not, I guess, not overuse the same symbol, you don't see the curly braces used as much. You could use, say, another set of brackets. So this happens sometimes in mathematics. But yeah, this won't mean f times x, even though it looks like it. It's really the symbol in and of itself. So I hope that helps. So to use this notation, it makes things a little more efficient, and efficiency is a big thing, especially if you have a lot of long calculations. So really, any little place where you can make things faster, but hopefully still understandable, helps. So let's say we want to find f of 3. So in this case, what you would do is say f of 3. So 3 is going into the factory, is 4 minus, and again, every x, if we replace the x here with a 3, that means all the x's are going to be replaced with 3's. So f of 3 equals -8. Or if you write this as an ordered pair, f of x equals 3, -8. That's going to be your answer. Questions about that? Let me do another one. We're running out of time. Well, we're a little over time, but spare me a little bit more. We'll try to wrap this section up. Let's say we have this.
I'm sorry, I missed the last part of that. Okay, so you had f of 3, and then it equals -8, and then you had
It's x f of x.
okay.
That's 3, -8. And this is going to be important. We're going to look at graphing a function. And it's the same thing as graphing an equation, but we're just going to use a different notation. But you have your input of 3, and you have an output of -8. Any questions about that?
No.
So let's say you have this. Let's say you have a function that looks like this, and this is a plus sign with some t's. And so we're going to find g of 2. So what's going on here? We're replacing the t with the 2. So that means g of 2, everywhere where there's a t, we're going to put a 2. And that's it. We replace all the t's with 2's. So this means we have 2 plus 4 over 5 or 6 fifths. That's going to be our answer. Questions about that? So the last thing to mention here, let me just check the homework real quick. I want to see if they're going to dig too much into the terminology here. I don't think they are. There is one thing on the homework I do want to mention. Okay, so what does come up, and you might have heard of this before, but it's a concept called domain. And what domain basically is, it's all the possible inputs. A domain is all the possible inputs. Now, so far the functions we've worked with the exception of this g of t here, and I'll explain why, there were no limits on the inputs we could use. And the idea is this. Some inputs are not usable. And this might seem kind of strange. But if you think about the analogy with the factory, so you're putting trees into this paper factory, and as a result, it generates paper. So in that case, let's say you decide to use what's called, it's a rubber tree. And they basically, I want to say they're indigenous to, I think, Asia, and they're being raised, I think, in Brazil. I might have that backwards. I apologize if I do. But you can cut rubber trees, and actually there's a resin that comes out of them that's rubber. And if you put this into your paper factory, well, it depends if your paper factory can handle rubber trees. Lots of paper factories can probably handle trees that are whatever their company is using. So is there special equipment you have to process different trees? So there might be something that's off limits. For example, for our paper factory, well, let's say you don't use trees, you use boulders. That's right. So when you pull up and you say, I'm going to try this out. I'm going to take this big boulder and chuck it into the machinery and see what happens. Probably nothing good. Tear everything up. So there are some inputs we really can't use. So let's take a look at g of t. We had t plus t squared 7 minus t. Is there a number that's going to make something go wrong? And when things go wrong with math, things that we tend to look out for, division by 0, the square root of a negative number. Now, this one's not always a problem. When you get into complex numbers, or as they're sometimes called imaginary numbers, they, this can work. But when you get a division by 0, that's considered undefined. And if you're working with real numbers, you can't take the square roots of negatives. And there are other restrictions. There's certain things mathematically we don't try to do. So if you take g of 7, so we replace all the t's with 7s. We get 56 divided by 0. And for us, this is undefined. This is something we don't do in mathematics. We kind of think of it like this. If I have $56, or we'll say there exists $56, and you're going to divide that amongst nobody, what do you get? What's the result? And remember, you think about division, like let's say we have $56 and we divide it between 2 people. Well, that would be 56 divided by 2, that's going to be 28. So if you take $56, give $28 to one person and 28 to the other, well, the answer of 56 divided by 2 is 28, the amount of money each person has. So here's a philosophical question. How much money does each person get if there's nobody there? Because you might say, well, 0. And I'll say, well, hold on. If you have $0 and you divide that between 2 people, you can't give either one anything. So they walk away with $0. But how much money do people walk away with if at the same time they're not there to walk away to begin with? So this is, we call this undefined. So what does this have to do with domain? Well, this says 7 is not in the domain of g of t. So it's not one of the allowable inputs. This is showing up to your paper factory with the boulder and chucking it into the machinery. So 7 won't work. So that's the idea of domain. Then we have range. What range is? All the possible outputs. So basically, once it's all the numbers we get by putting in all the values of the domain or all the inputs into the function. So it's the outputs we get if we use all possible inputs. So let me do one example with domain and range, and then I'm going to do an example graphing a function, and then that's going to be it for today because we're going a little long.
I'm going to be right back. I'll be right back, just real quick. But go ahead and continue since it's recording and stuff. If I need to go back, I'll just look at the video.
Okay, no problem. I'm just going to erase. So that's good. Now this might not appear, looking at the homework, it's not in the homework, but it is something that you could encounter in the future, is if you have ordered pairs, and can you identify values of the domain and values of the range? So let's say you have this.
Okay, I'm back.
All right, I'm just writing this first example. I'll wait for you to catch up. But what we're going to try to do, we're going to try identifying values that are in the domain and values that are in the range. And let's say we have 3 ordered pairs from some function f of x. And we might be asked to figure out what values are in the domain. What values are in the domain? Well, remember the domain are all the input values. So that means -1, 7, and 6. Because remember, these are ordered pairs. X, f of x. Input, output. So in this case, the answer would be -1, 6, and 7. So those are going to be values in the domain. Those are the values that are in the input position, or the x-coordinate, for each of these ordered pairs. Now let's consider this. What values are in the range? Well, in this case, we're looking at all the outputs. So there's a 7 that happens to be an output. There's a 4, and then this is the symbol for pi, or 3. You've seen this before, 3.14159, and so on. So the answers here will be pi, 4, and 7. And so if we're looking at ordered pairs, that's how we figure out values in the domain and values in the range. So questions about that? All right. So the last thing I want to do, let's graph a function, and we're just going to use function notation. It's going to be exactly the same thing as graphing an equation with two variables. So we might see this. F of x equals 2x minus 1. So we need to come up with some points. Now this is actually going to be a line. And we'll talk more about lines later. If you're not sure how many points you need, use more than 2. 2 points work for lines. For curves, you're going to need more than 2 points. But this is a line, so I'm just going to go for 2 points. So let's say we're going to come up with an ordered pair generated from x is negative 2. So that means we're going to have f of negative 2 equals 2 times negative 2 minus 1. And once again, this means multiplication, but this is a symbol. Negative 2 is going into the factory doors to be processed by this function over here. We get negative 5. And let's say we're going to go with x is 2. And here I'll not skip a step there. So we get 2 and 3. So we're going to graph these 2 points. And if it helps, again, you can exchange y and f of x. They symbolize the same thing. They're the output. So sometimes when you see this, you'll have an x-axis over here, and they'll sometimes just label it as x. They'll sometimes label this instead of y, they'll label it f of x. Oh, and I need to go a little farther here, negative 5. So once again, we'll start at the origin. Origin to negative 2, and then we'll drop down to negative 5. And then origin to 2, and then up to 3. F of x is 3. Let's see. I want to make sure I get my intercepts just 2x minus 0. double check this real quick. Oh. You just got to connect the 2 points is all that you got to do. Yeah, that's about right. And then you'll get your double-headed arrows. You just need to connect these 2 points, but for the accuracy of the graph, I wanted to make sure that I intercepted the y-axis and the x-axis appropriately. But no, when you're doing your graph, you don't need to think about it like that. First point, second point, you're good to go. So that's it. So if you have any questions, let me know, and that's section 10.1.